Hello, everyone. This will serve as the exam review for Unit 2. And so this covers everything from uh, doing derivatives using the chain rule, product rule, quotient rule, on up to where we start to do implicit differentiation. We study elasticity of demand, and we get into being able to do some curve sketching, studying when a function is increasing, decreasing, when it's concave down, concave up, and all those things. So wanted to go over this practice test via video so that you kind of get an idea of what you should be thinking as you do these problems. So let's go ahead and get started. So the first problem that we have here is we want to calculate the derivative of 9x squared divided by natural log of x. And so in looking at this, we see that we have 9x squared in the numerator, natural log of x in the denominator. So we will be doing the quotient rule to do this. And so to do the quotient rule, we know that it's going to be, I'll just do this in general here. If we call this, well, not f, because we already have that. So let me call this a and call that b. 9x squared, we'll say that's a, natural log x, call that b. So we're going to say low times derivative of the high function minus high times derivative of the low function divided by the low function squared. Or for short, we just say low d high minus high d low over low squared. So in looking at it that way, when we take the derivative, we will take the low function times the derivative of the high function, and I'll do this in prime notation, minus high function times derivative of the low function all over the low function squared. And so when we take the derivative of 9x squared, that's just going to give us 18x. So we'll have 18x times natural log of x for that first term, minus, and the derivative for natural log of x is just 1 over x. So we'll have 9x squared times 1 over x. Of course, all that over natural log of x quantity squared. The only other thing we can really do here is we know the x squared and 1 over x, that reduces to just x. So we have a 9x here. And if you notice, 18x is basically 2 times 9x. So we have a common factor of 9x in both terms. So I'll go ahead and factor that out. What we have left is just 2 times natural log of x here, minus 1, and then that over natural log of x quantity squared. And that's pretty much all we can do with that. If you wanted to keep your answer as 18x times natural log of x minus 9x over natural log of x quantity squared, then that's fine as well. The only reason why I separate it like this and factor it out in the numerator is because, and you'll see later on in this test, we will be asked to find stuff like when is a function increasing, when is it decreasing, when is it concave up, when is it concave down. And if we can, and particularly in the cases where we want to find when a function is increasing and decreasing, if we use test intervals, one of the things that we want to know is when is the function constant, or where do we have a critical value, or put another way, when do we have a peak or dip in our graph. And so if we look at it that way, if we solve this equation, then we're trying to figure out where we have horizontal tangent lines. So if we use the test interval method for that, then let's say at some x equals a, we have that, then we can test to see if we plug in a value that's less than a into the derivative, we may get positive value. And if we plug in a value that's greater than a into it, we get a negative value, then that tells us that we have a peak there. We could also use the second derivative test and take our critical values that we get from the solutions here and plug it into the second derivative and figure out whether we have a place where the graph's concave up, concave down, and thus we can also figure out whether we have a local min or local max. So it has nothing to do with this problem, but I wanted to say all that because that's the reason why we would want to try to factor this out if we can. Because in this instance, if we need to find out what f prime of x is equal to 0, then here we would just take the numerator and set that equal to 0, which means we would say 9x is equal to 0, or 2 times natural log of x minus 1 is 0. And then from there, we could just solve both of those equations to figure out the values of x that meet that. And then we could use the test intervals here, which is known as the first derivative test. So that's problem number 1. Let's go ahead and move on to problem number 2. So we want to find the slope of the tangent line to the graph of this particular relation at the point natural log of 7, 5. And so notice that this is not a function. And it's not a function because if I tried to take that equation and solve it for y, I will see that y will be in terms of x as well as y. And one of the things that we know about functions is that a function cannot be written in terms of itself. So here what we would have to do to figure out what the slope of the tangent line is, and anytime we want to find the slope of a tangent line, we're basically trying to find a derivative. So the slope of the tangent line for this case is going to be what y prime is when x is equal to natural log of 7. Okay, or in particular, I'll write this another way. Let me erase this. We can also write it at when we want our point to be natural log of 7, 5, where this is going to serve as my x value, that's going to serve as my y value. So we have to differentiate this equation implicitly. So we're going to start off by taking the derivative of both sides with respect to x. And let's get all that down right quick. All right, and so from here, we notice that anytime that we take the derivative of each term in our equation and the variables match, we do the derivative as normal. But whenever the variables don't match, like in the second term here, we would have to do the chain rule, okay, where necessary. So if we look here, the derivative of e to the x with respect to x is just e to the x. So I'll just come here and then minus. We know that here the derivative of y with respect to x, we would have to use the chain rule. And if we did this the long way, we would say the derivative of y with respect to y is just 1 times the derivative of y with respect to x would just be dy over dx. But in this case, since y prime is what dy over dx is, we will just call this dy over dx and leave it like that. On the left side, of course, the derivative of any constant is 0. And now when we take the derivative of natural log of y minus 4 with respect to x, again, we're going to have to use the chain rule here because the sign, not signs, but the variables are different. In addition to that, we see that natural log of y minus 4 itself is a composition function. So we're going to have to use the chain rule for that reason too. So when we take the derivative of this, we would say, what is the derivative of natural log of y minus 4 with respect to y? And that would just be 1 over y minus 4. But then we have to multiply that times the derivative with respect to x of y minus 4. Okay? So that's where the chain rule is being utilized. So if we come down here and make a new line, we know that this is just e to the x minus y prime. And I'm just simplifying dy over dx to y prime. And that will be equal to just 1 over y minus 4 times, and now we actually need to take the derivative of y minus 4 with respect to x. So in the first term, if we just do the derivative of y with respect to x, of course, it's just going to be dy over dx, and minus the derivative of any constant is 0. And so this we can just simplify to y prime. So now this tells us that e to the x minus y prime is basically equal to y prime divided by y minus 4. And so from here, if we multiply both sides of our equation by y minus 4, then we get y minus 4 times, did not do that correctly. So I need to separate all terms that have y prime first. So I would want to add y prime to both sides here. And if I do that, I get e to the x equals y prime plus y prime divided by y minus 4. So I'm going to scroll down a bit here, make some more room. And so now my next step, and I'll just come here and do that, I would want to factor out y prime, which will give me just 1 plus 1 over y minus 4. And thus, y prime would just be equal to e raised to the x divided by 1 plus 1 over y minus 4. And of course, if you wanted to, you could make this expression a bit more clean by multiplying numerator and denominator by y minus 4 if you wanted. Not necessary though. So now we know what y prime is, and this would imply that the slope of the tangent line is going to be the same as y prime evaluated at natural log of 7 at the point natural log of 7, 5, where this is going to be our x, that's going to be our y. So let me scroll down a little more to give us some more room here. So therefore, slope of the tangent line is just going to be e raised to the natural log of 7 divided by 1 plus 1 over, let's see, 5 minus 4. And e raised to the natural log of 7 is just 7. And we have 1 plus 1 divided by 5 minus 4, which is just 1 over 1. So that just ends up being 7 over 2. And so that would be the slope of our tangent line at the point natural log of 7, 5. All right, so let's move on to the next problem. All right, so for our next problem, we want to figure out or we want to find the absolute maximum and or minimum value for the given function if it exists. And to sort of have some intuition on what's going on with this particular function, we have to go back to pre-calculus or college algebra. And the first thing that we want to note is that this is a rational function. And it's a rational function where the degree of the numerator is larger than the degree of the denominator. So we have an instance here where we're going to have an oblique asymptote. And so the oblique asymptote, since the difference in between degree of numerator and denominator is 2, is going to be quadratic. Okay, so that sort of makes this problem a little different in that we know that if we find out what the oblique asymptote is, we'll kind of see what the end behavior of the function is. We also know that we have a vertical asymptote at x equals -1 because that is what makes the denominator 0 here. Okay, and so we would need to take that into account. Now, let's just look at what the oblique asymptote would be. And so to find that, we would take 3x cubed and divide it by x plus 1. And when we look here, we know that x goes into 3x squared, 3x cubed, 3x squared times. And so from that, if we did the whole polynomial division thing, that would be cubed and that would be squared. And then we would have to subtract. So then that would go away. We would just have this. So now we would do it again. And we would say x goes into -3x squared, a -3x times. So we would have -3x squared minus 3x. And then we would have to subtract by changing the signs. And we would just have 3x there. So my point here is that we could rewrite this as 3x squared minus 3x plus 3x over x plus 1. And so this gives us an idea of what the oblique asymptote is going to look like. Now, in terms of calculus, we know that this portion, that graph is going to look like a quadratic function going up. So if we take the limit as x approaches infinity of this function here, no matter how we try to rewrite it, this is eventually going to go to infinity. And the same exact thing is true when we do this for, or as x approaches -infinity. So what this tells you is that from here that we have no absolute maximum, okay? So we know that. Now, in terms of an absolute minimum, of course, absolute minimum means what is our lowest point on the graph. Remember that we said we had a vertical asymptote at x equals -1. And so for vertical asymptotes, we normally know that the graph either goes down to -infinity or up to +infinity, okay? And so in this instance, to sort of get an idea of how this graph is going to act, and this actually comes from college algebra pre-cal, if we took f and we plugged in -1 into it everywhere except for where it makes the denominator 0, then we would have this case. And of course, this looks like just a -3 over x plus 1, which basically looks like this. And so what this means to us is the following. We know from graphing transformations that -3 times 1 over x plus 1, 1 over x plus 1 looks like 1 over x, and 1 over x is a function that looks like this. And I like to call it the wax on, wax off function. But since we have a negative number being multiplied by it, it will look more like -1 over x, which will be going this way. So here at your vertical asymptote of x equals -1, you have this type of behavior here. So what that means is that whenever we take the limit of the function as x approaches -1, of course, if we look at it from the, let's say if we look at it from the left here, then we know that that's going to go up to positive infinity, because that's kind of what we're seeing here. If we do the same thing, approach -1 from the right for this particular function, then we know it's going to go down to -infinity. And so what we're seeing here is that even though we will have some type of local minimum, or in this case, yeah, we will have a local minimum and or local maximum, we're not going to have an absolute one, okay? And the reason is we have a vertical asymptote here, so the graph keeps on going up to positive infinity, down to -infinity at x equals -1. And we also know from what we saw earlier that as x approaches positive and -infinity, because of the oblique asymptote that we have, it's going to go up to positive infinity itself. So in this case, we would say that there is no absolute max or min. And so on your exam, what you need to show as a minimum, you need to show that the limit of this function here as x approaches positive or -infinity would go up to infinity. And you would also need to show here that you would have this case here. And so this would mean no absolute minimum. And so then if you show this, show that, and then you conclude with this answer here, then you're pretty much good to go. Everything else that I've done here, like showing you the vertical asymptote, giving you this little strategy to kind of figure out the behavior around the vertical asymptote, and doing the dividing the function so that you can explicitly see what the oblique asymptote is. That's just background information I'm giving you to sort of help guide your thinking there, okay? All right, so let's move on to the next problem. All right, so for our next question, we suppose that we have price, which is represented by P, that's in dollars, and demand, X, of pencils is given by the equation here. So we're basically given a price or price demand equation, and we want to know for what values of P is demand elastic, and what does this apply about the revenue at these prices. So the first thing that I want to do is bring you back to some concepts about what the elasticity of demand actually is. Now, in general, the equation for elasticity of demand is the following. So we say elasticity with respect to price is negative of price times derivative of the function that we're talking about with respect to price over the function itself. Now, since we have a situation here where we can take X and we can define it in terms of P, for our situation, this will look more like this. Okay? And so to do that, then we would take this equation and subtract both sides by 5,000 P squared. And if we did that, then that would be 30,000 minus 5,000 P squared. And if we factored out of 5,000, then that would be 6 minus P squared. All right, so now we have a way to be able to express X in terms of P. So I want to take a pause here and actually go over some of the notes so that you know what we're asking, why we're asking it, and how to simply come up with these answers here. All right, so when we talk about elasticity of demand, what we're actually talking about is how does our demand fluctuate with respect to price, okay? And so we have three categories. The first is demand is inelastic, and we know that whenever the elasticity of demand that we calculate at a particular price point is in between 0 and 1. This says just less than 1, but normally we do not talk about negative elasticity of demand. So in all actuality here, this is actually in between 0 and 1. And so when we say demand is inelastic, that means that whenever we have a change in price, that does not change the demand that much, okay? And to kind of give you a scenario to where this makes sense, let's say we wanted to go to McDonald's and buy, let's say, a large fry, okay? Large French fry. And in that instance, let's say that the large French fry cost, I don't know, let's say $2, okay? If we change the price, in other words, if McDonald's wants to raise the price from $2 to $2.05, if demand is inelastic, then that means that their price change was small enough not to affect demand that much. So the same people who bought the large French fry at $2 would probably also buy it at $2.05. You may have a few people that drop off, but it's not that big of a price change. Okay. Now, in the case of demand being elastic, then demand is actually sensitive to price changes. So let's say if we were talking about, all right, the large French fry costs $2, and now let's say we have an instance to where they raise the price from $2 to $2.50. Then of course, $2.50 may be too much for a lot of your people who normally buy that particular food to pay for it, because they're like, all right, $2.50 is not worth that. So you're going to have a drop off in demand. We could also go the other way, and so we can say that we would drop the price from, let's say, $2 to, let's say, $1.40. Then of course it'll affect demand because more people will be like, all right, I'm getting a bargain. So there will be more people who were not willing to buy it at $2 that's willing to buy it at $1.40. Okay, and so in that case, demand is elastic. And then of course, unit elasticity means that the change in price produces the same change in demand. So to put some numbers by this, let's say if the price goes up, let's say 1%, then, well, let me make that a little bit more realistic. So let's say the price goes up 10%, we may have a change in demand going down by 1%, okay? Whereas in this case, let's say the price goes up 10%, and by that, the demand goes down by, let's say, 20%. So the way it was priced before was right at the critical mass of people who were wanting to buy it, who were not wanting to buy it. So once we pass that threshold, any small change in price would actually make demand go down a lot. And so here in this case, if we have prices went up by 10%, then that means the demand, let's say, would go down by 10%. And so percentage-wise, this is what it means to talk about elasticity of demand. All right, so if we look at this as a whole, from a graph standpoint, this parabolic curve here is going to be revenue in terms of price. And so we see at a particular price point here, which would be P, if our price decreases, then that means we have decreases in revenue. And of course, this is endemic of whenever we have inelastic demand, okay? Since the percentage change in demand is not that much, then of course, if you decrease the price, your revenue goes down because you got mainly about the same amount of people buying the product. If your price increases, then your revenue increases, because again, demand is such that it's going to be relatively the same. It's not going to be exactly the same, but the change in demand is small enough to where you roughly have about the same amount of people purchasing the product, but yet your revenue is going to go up because they're paying more for that particular product now. Now, we also see that when demand is inelastic, the rate of change of revenue is positive. And remember, when we talk about derivatives, derivatives just track the slope of tangent lines. So this is another way of saying that your revenue is increasing. And we know that because the slopes of the tangent lines for all these points here are positive. Now, when demand is elastic, we know that because the elasticity of demand is greater than 1, and we have decreasing revenue. So that means at this price point here, if you decrease the price, then your revenues increase. And because you're at a point now to where the price is low enough for more customers to want to buy it, and thus your demand is increasing. However, if you go the other way, if you increase the price, then your revenue decreases because you have people dropping out and saying, well, that product is too expensive for me. Okay? And of course, here we see that revenues are decreasing because, again, the slopes of the tangent lines for this portion of the graph are negative. And then unit elasticity would be right here in the middle, okay, where the slopes of the tangent line are horizontal, and elasticity of demand there would actually be equal to 1 at that point. Now what I have here is I've taken all that information and I've just put it in a table form so that we see that when demand is inelastic, as prices go up, revenue goes up. And as prices go down, revenue goes down. And we see here that the change in revenue is going to be positive, meaning that revenue increases. So when demand is elastic, then as prices go up, revenue goes down. And as prices go down, revenue goes up. And of course, at this phase, revenue is decreasing. And then of course, for unit elasticity, we see as price goes up or goes down, there's no real change in revenue. So the change in revenue is constant at this point. All right, so now that we have an idea of what elasticity of demand is, we want to know for what values of P is demand going to be elastic. And so what we're really asking in this case is, when is elasticity of demand going to be greater than 1? And so what does this imply about the revenue at these prices? Well, one of the things that we know is that when elasticity of demand is greater than 1, the rate of change of revenue is decreasing. So we already know that. So now we just need to find out what values of P actually satisfy this. All right, so the first thing that we want to do is just find out what the derivative of X is in terms of P. So let's go ahead and find that out. And so if we take the derivative of 5,000 times 6 minus P squared, 5,000 is constant, so we ignore that. That'll be multiplied by 0 because the derivative of 6 is 0. The derivative of P squared is just 2P. So we will have 5,000 times a negative 2P. So if we fit that into our elasticity of demand equation, then we have a negative P times 5,000 times a negative 2P. And all that is going to be over the original function for X in terms of P, which is 5,000 times 6 minus P squared. So here we see, we see that 5,000 is reduced to 1. We see that a negative times negative is a positive. And so we have 2 p squared here over 6 minus p squared. And so remember that we want the elasticity of demand here to be greater than 1. So our goal here is to have this be greater than 1. Excuse me. And so here what we could do is basically take this and subtract it by 1. And then of course that'll make it look like whenever this new function here is strictly above the x-axis. And here we can rewrite 1 as just 6 minus p squared over 6 minus p squared. So if we did that, then this is what it would look like. 6 minus p squared over 6 minus p squared. And this would just be 2p squared minus 6 plus p squared, because we have to distribute negative there, and all that over 6 minus p squared. And that will end up giving us 3p squared minus 6 all over 6 minus p squared. And that would have to be greater than 0. And so when we look at this, we're looking at this as a rational function, where we know the only places where a rational function will change sign from being having positive y values to negative ones would be either at an x-intercept or at a vertical asymptote. And of course, for our x-intercepts, we would need to figure out where our numerator is equal to 0. So what values of p, where they equal 0. And of course, for the vertical asymptote, same thing, where the denominator equals 0. So we would want to figure out what is the solution to this equation, as well as what is the solution to this equation. So of course, if we come and solve for the x-intercepts, then that would be 3p squared is equal to 6. We divide both sides by 3, and we just have p squared is equal to 2. And thus p would be plus or minus square root of 2. And from here, we would just consider the positive value for that. So that's going to be one of our partition values. For vertical asymptote, 6 minus p squared equals 0 here. So this would end up being 6 is equal to p squared, which would mean that p would be equal to plus or minus square root of 6. And again, we would only consider the positive value here. So in looking at this, we're going to, I'm going to use the test interval chart to be able to do this. And we'll see that the two partition values that we're going to have is at square root of 2 and at square root of 6. All right, so let's go now and make a little bit more room so that we can do our test intervals here. So now that we know what our partition values are, and we know that for pricing, we're not going to go below 0. So start here at 0, and then do square root of 2, and then here do square root of 6. And we know that for both of these, that since we're being asked when is this function strictly above the x-axis, so that's what the greater than or greater than 0 means here in this case, we know that we will not include the 0, we will not include the square root of 2, and we will not include the square root of 6 in our answers here. So what I'm going to do is I'm going to do an open circle around all of these to remind myself of that. And so now all we need to do is look at our function here, which we're going to look at it in this form. and use that to be able to figure out when we have for certain values of p, it's going to be positive or negative. So I'll just go ahead and rewrite it over here. So in the numerator, I can factor out a 3, and that will just give me p squared minus 2. And erase that. And in the denominator, we'll keep that the same. And so now we want to choose some test values. So square root of 2 is roughly around 1.41. So we'll just use a simple test value of 1 here. And I know that square root of 6, that is more than square root of 4, which is 2, but it's less than square root of 9, which is 3. So I will just use another test value here, 2. And of course, we can come here and do 3 for here. So we'll just use those 3 test values. So at p equals 1, if I were to plug this into here, then of course I know that this 3 here is always going to be positive. If I evaluated this at 1, then I would have 1 squared, which is just 1, minus 2, and that would give me a minus 1, so that would be a negative number there. Okay. And so if I also plug in a 1 here, then I would know I would have 6 minus 1, which is 5, so that would be positive. So positive times a negative divided by positive ends up being negative. So I know for this portion, this would be below the x-axis. If I had it at 2, then if I plugged in a 2 right here, then 2 squared is 4, and 4 minus 2 is 2, so that ends up being positive now. So we know that our numerator is all positive, and if we plugged in a 2 here, 2 squared is 4, 6 minus 4 is 2, so that would be positive as well. So here we would know inside here that it's going to be positive. And for some reason my pen's not writing, but let's see if I can fix that. All right, so I think we got that fixed now. So that would be positive in between square root of 2 and square root of 6. So lastly, we would try when p is equal to 3. And so when we do that, and I'll just go ahead and erase this and erase that. We plug in a 3 here, then that would be 3 squared, which is 9. 9 minus 2 is 7, so that's going to be positive. And if we came and we substituted in a 3 for p here, so 3 squared is 9, and 6 minus 9 is a negative 3, so that would be negative in the denominator. So positive times positive is positive, but dividing by a negative is being negative. So, and what we see here is that our demand, if we go back to the original problem, we were asked to see when our demand would be elastic. So our demand is going to be elastic in between these prices here. So when the prices are in between square root of 2 and square root of 6, we know that demand is elastic, okay? And that just means that if we have a small percentage change in price, that's going to be a huge percentage change in the amount of demand. And of course, like we stated before, we know that in terms of the revenue will be decreasing. The rate of change of revenue will be decreasing at those current prices. Okay, So that's how we do that question. So let's go ahead and move on to number 5. All right, so looking at this graph, we have a graph of revenue, and we want to know for what values of P is demand elastic. Well, one of the things that we know from our previous problem is that if demand is elastic, then the elasticity of demand is greater than 1, which tells me that the rate of change of revenue is decreasing. Okay. We know that if the elasticity of demand is in between 0 and 1, then it is going to be inelastic. Of course, this part here is elastic. So inelastic, which means that the rate of change of revenue is increasing. So right here at 40, we have unit elasticity. And over here, the slopes of the tangent line are increasing. So this is where it is inelastic. And of course, that means on this side, slopes of the tangent line are decreasing. So this is where it is elastic. So we could look at this way and basically say when prices are in between 40 and 80, we know that the demand is going to be elastic. Now, some of you may want to say when the prices are greater than 40, that is fine, but know that realistically here past 80, we get into negative revenue. And so realistically speaking, we wouldn't be operating in a sense to where we're actually losing revenue at that point. Okay, so that's why a more realistic answer would be for values in between 40 and 80. All right, let's move on to number 6. All right, so for this question, we're asked to look at the given information, and from that, we want to sketch a possible graph. And so what I'm going to do is just draw the properties and then just fill it in with something that I just come up with. The main thing that you need to be worried about here is what this means. So I'll just label these A, B, C, D, E, and F. Okay. So for A, what that's telling me is that I actually have the point -2, 2 on your graph. So if we look here, we know that we have this defined point on the graph. For B, this is telling me I have the defined point to -1 on the graph. So that would be here. For C, what that is telling me is that at x equals 0, I have a horizontal tangent line. Okay, so I have horizontal tangent line at x equals 0. And so we could come up with various ways to put that. But if you see here for E, we have an inflection point at 0, 0. And so an inflection point means we're changing concavity. So we're either going from concave up to concave down, or concave down to concave up. Okay. So E tells us that we have a point here, but at this point is all the concavity is going to change. And we know that we're going to have some horizontal tangent lines. So I'm just going to draw it like that. So C tells us that we have a horizontal tangent line here at x equals 0, and we know that we're going to be changing concavity. And from what it looks like we'll be coming from this point to this one to that one. And so depending upon how the concavity looks, that will give us the information that we need to know. So we've taken care of E, so that means inflection point, concave up to concave down, or concave down to concave up, depending upon what the graph's going to look like. Okay. For D, what D is telling us is that our graph is either going to be increasing or constant for all values of x, okay? So decreasing or constant for all values of x. So the graph has to basically be going down like this or flatten out for all values of x there, okay? So if we're looking at it this way, one of the ways that we could actually draw this graph here is to kind of make it go down like this and then can make it continue going down there. But F is actually going to sort of rein in everything. So we see that we have a horizontal asymptote at y equals 3 and at y equals negative 2. So y equals 3 is here and y equals negative 2 is here. So we have these horizontal asymptotes. And so with that, we can kind of get an idea of how this graph's going to look now. So now that we have all this drawn, I have changed colors here so that we can kind of see how all this is going to work. So we know that this graph has to be decreasing, and since we have a horizontal asymptote here, we're going to have to ride along horizontal asymptote up here. Since we're decreasing, we know we have to go down like this, so that's why I'm starting up here like that. And then I can go through this point and come here. And so I see for all this, the graph's going to be concave down. And then here, from this particular point, I could go from flatten out and then kind of come like this again. I know I have to come through this point, eventually do like that. So want to make sure that we keep everything in play here. So we know we have to have an inflection point, and we know that we have to have a horizontal tangent line here at x equals 0. So I'm actually going to erase this because I think I have a better way I can draw it. So here, what this could come up being is, let's say we know that this is going to have to kind of come and do like that, and then that would do like this, and then come like that. And then for here, this could, you could have this point here, go through here, and kind of do like that. And so this graph would satisfy all the conditions that we need. So to review, we have the point negative 2, 2 on the graph. We have the point 2, negative 1. We know that at x equals 0, the slope of the tangent line is going to be 0, which means we have a horizontal tangent line. The graph is always decreasing or constant for all values of x, and we've met that. We have an inflection point at x equals 0, and in particular, this portion of the graph from negative 2 to 0 is going to be concave up, and from 0 to 2 is going to be concave down. So we've met that condition. And then we have the horizontal asymptotes at y equals 3 and negative 2. So that's how this graph would look. All right, let's move on to number 7. Okay, so for number 7, what we want to do is figure out where the following function that's given to us, which is 6 times e raised to the x minus 2 times e raised to the 3x, is concave down. And we actually want to find the x and y coordinates for all of our inflection points. Okay? Now, just so that we make sure that we understand what this question is actually asking for and the background information for it, we know that an inflection point is the location where concavity switches for a particular function. So an inflection point is a defined point on the graph where we go from concave down to concave up, or we go from concave up to concave down. And how we will actually find where those inflection points are is we will take the second derivative of our function and set it equal to 0. And the values of x that satisfy this equation will be the values where we will have those inflection points, provided that the function is actually defined at those x values. Since we have two terms in our function that is basically an exponential function, then we know that the domain of this function is all real numbers, and therefore we know that whatever values of x that we find for the second derivative, the original function will be defined there. An instance to where we would have a situation where concavity switches, but the function is not defined there, would be at a vertical asymptote, for example. So let's say we had a function and its graph kind of looked like this. Let's say it was concave up from there, concave down there. And this was at, let's say, x equals 6, where your vertical asymptote is. Then the graph goes from concave down here to concave up, but the vertical asymptote location would not be considered as a place where we have an inflection point, because again, the function is not defined there. So that's what we mean by that. Okay, so now let's go ahead and find out what our second derivative of our function is going to be. And then from that point, let us set it equal to 0 and solve for those values of x where we are expecting our inflection points to be. So let's take the first derivative. So for our first term, we ignore the constant, and the derivative of e to the x is just itself. So next we'll do the minus, and then we ignore the constant 2. And then when we take the derivative of e to the 3x, we realize that e to the 3x is a composition function. So we're going to have to take the derivative of e to the 3x using the chain rule, which kind of looks at 3x as just some single variable like u, and we'll just say the derivative of e to the u with respect to u is just e to the u, where u is equal to 3x. If we wrote that out the long way, it would look something like this. So say the derivative of y with respect to x would be the same as the derivative of y with respect to u times the derivative of u with respect to x. And of course, y in this case would just be e to the u. So if we wrote that out, it would look something like this. And of course, u is just 3x. So once we're done, derivative of all this is just e to the u, and derivative of all this is just 3. So we just end up with 3 times e to the u, and u is 3x. So just doing that the long way this time, I won't do that again, but just explaining why here when I say what is the derivative of e to the blah, I'm just going to say e to the blah times what is the derivative of the inside function, which is 3x, that would just be 3. And you see that that essentially gives me the same thing. So I have 6 e to the x minus 6 e to the 3x. And from there, I'm going to factor out 6 e to the x. That would just leave me with 1 minus e to the 2x. And of course, again, how I get that, if I have e to the 3x, that's the same as saying e to the x plus x, which is the same as e to the 2x plus x. And I know that I could rewrite that as e to the 2x times e to the x. And of course, I just factored out this one factor of e to the x there and left the e to the 2x remaining. So that is how we get what our first derivative is. So I'm going to use this form of our first derivative for the second derivative. So to do that, here I know that the derivative of 6e to the x again is just 6e to the x. and that the derivative of e to the 3x, because we're going to ignore the constant here, is again going to be e to the 3x times 3. And of course now we see that would be 6 e to the x minus, in this case, 18 e to the 3x. But I'm just going to rewrite it this way as 3 times 6 e to the x e to the 2x. And I'm doing it like that because I see I have a common factor of 6 e to the x again. So when I factor that out, that's just going to leave me with 1 minus 3 e to the 2x. And so this is what I need, because I need to take that and set it equal to 0 so that I can find those values of x that have that satisfy that equation when I set it equal to 0. So I know that if I take the second derivative, set it equal to 0, then that means that 6 e to the x times 1 minus 3 times e raised to the 2x is going to be equal to 0. Okay? And so from that point, we know the following. We know that this means that 6 e to the x is equal to 0, or we know that 1 minus 3 e to the 2x is equal to 0. And so for our first equation, the answer to this is going to be no solution. And we know that because the graph of 6e to the x just kind of looks like an exponentially increasing function, and we have a horizontal asymptote at y equals 0, which tells us that there is no value of x that will make 6e raised to the x equal to 0 for its corresponding y value. So answer to that first part is no solution. The second part, or second equation, we'll just add 3e raised to the 2x to both sides. Oops, let's get that fixed there. E raised to the 2x, divide both sides by 3. And you see from here, we could either take the natural log of both sides, or we can do the direct translation. I'm going to do the direct translation for this one. And so that would be 2x is equal to natural log of 1/3. And if we do that, then of course, if we divide both sides by 2, we would get natural log of 1/3 divided by 2. And so that is what that value of x would be, where we have an inflection point. And so to make this a little bit more clear, I'm actually going to rewrite it this way. And by me doing that, I could put this as natural log of 1/3, all of that raised to the 1/2. And that would essentially just be natural log of 1 over square root of 3. Okay? And if we wanted to go a little further, I know that I can use my logarithm properties to essentially say that this is going to be natural log of 1 minus natural log of square root of 3. And that's 0. So this ends up just being negative natural log of square root of 3. So I'm only doing that so that you know what type of number or numbers we're dealing with. Okay. And so we have x is equal to negative natural log of square root of 3. And so this would be the location of our inflection point. And so now what we're asked to do is to find where the function is concave down. So that's one thing. And the other thing that we're asked to do is to find out what is going to be the corresponding y value for this particular value. And so we are going to verify that this is indeed an inflection point by doing the concavity test, which is we're basically going to use test intervals to show that concavity switched at that particular value of x. So I'm going to make us some more room here, and then we'll complete this problem. All right, so now that we have a little more room, we can go ahead and finish this problem. So the first thing we want to do is show where the original function f of x is concave down. So to do that, we're going to use the concavity test, which is using the test intervals. So we know that this is going to be where our inflection point is going to be. So just going to make number line here, and we're going to put negative natural log of 3 there. Okay, just so that you know, negative natural log of square root of 3 is about negative 0.549. Okay, so just to kind of give you a reference to what that value is. The reason that I'm keeping everything in natural log is that I noticed that whenever I plug in values for x, I'm going to have x in the exponent. So we know that e raised to the natural log of whatever I plug in here is just going to be x. So it actually makes it easier for me if I keep everything in natural log form to make that happen. Okay, so that's why I'm doing that. And also at this time, just using a little foresight here, we know that when we have this negative on the outside of the natural log, that's just the same as saying negative 1 times that. So I could go a little further and actually say that this is the same as natural log of square root of 3 raised to the negative 1, which is the same as natural log of 1 over square root of 3. And of course, if I look at it that way, then it actually makes doing the calculations easier whenever I plug in everything. All right, so here I need to choose 2 test values. And so I think the easiest test value to choose here on the right side would be 0. All right, so let's choose 0 here. And 0 is the same as natural log of 1, by the way. So, and over here, let's say we want to choose value that's a little bit more negative than this. We know that square root of 3 is like 1.732. So if I use natural log of 2, of course 2 is larger than 1.73. So negatively, that's going to be small. So we would just have that being a negative natural log of 2, which of course is the same thing as a same as natural log of 1/2. Okay. So anyway, so those are going to be our test values, and we are just going to plug in these values into our second derivative to find out whether the answer is positive or negative. And just so that we know, if the second derivative for some value of x ends up being positive, then we know that the graph was concave up for those interval of x values. And if the second derivative for a particular x value ends up being negative, we know that it's concave down for that particular set of x values. All right, so just going to go ahead and start with our first value, which is, we'll just write it as natural log of 1/2. So we'll say f prime of natural log of 1/2. We write that, then that will be, and remember we're using the second derivative here, so this will be 6e raised to the natural log of 1/2 times 1 minus 3e raised to the 2 times natural log of 1/2. Okay, and of course the e raised to the natural log of 1/2 is just 1/2. So we just have 6 times 1/2, which will be 3, and we'll take care of that in the next step. for the e raised to the 2 times natural log of 1/2, we can look at it this way. I'm saying e raised to the natural log of 1/2 here, all that raised to the power of 2. And of course, this is just 1/2. So we end up with 3 times 1 minus natural log of 3 raised to the 1/2 squared. And of course, all of that is just 3/4. And so you can quickly see here that this value is going to be a value that's greater than 0. No need to calculate what it actually is. So this means that our graph is going to be concave up at x equals natural log of 1/2. So we know here it's going to be positive, which means concave up. And so now if we do the same thing for f double prime of 0, because that's what, of course, we know that's the same as natural log of 1, then it's just 6 times e raised to the 0 times 1 minus 3 e raised to the 2 times 0. Of course, all of that is just 1. So we just have 6 because this is 1 as well. 1 minus 3, and we know that that's going to be negative because 1 minus 3 is a negative 2. And of course, that tells us that we're concave down at x equals 0. So negative here, which means concave down. So our question was, when is our graph concave down? So now that we know that, we can answer our first question, which is f of x is concave down when, and we're going to put it in this interval here. So this will be for values of x negative natural log of square root of 3 on to infinity. And of course, you could also write that this way as well. That would be perfectly fine. So this is the answer to our first question here. Our second question is, we needed to find out what our actual x and y coordinates are for our inflection points. Okay, so we know that this particular x value here is the x coordinate for the inflection point. So all we need to do now is take the negative natural log of square root of 3, or if we want to write it this way, natural log of 1 divided by square root of 3, and plug it into our original function here. So we'll make some room and complete this problem by finding out that corresponding y value. All right, so if we recall, our original function is just 6e to the x minus 2 times e raised to the 3x. And so knowing that, we are going to now plug in f of natural log of 1 divided by square root of 3. And this will be 6e raised to the natural log of 1 divided by square root of 3 minus 2 times e raised to the 3 times natural log of 1 divided by square root of 3. And of course, here we know that this is just 6 times 1 divided by square root of 3. And we could rewrite this as 2 times e raised to the natural log of 1 divided by square root of 3. All of that being raised to the 3rd power. And this is just 6 divided by square root of 3 minus, this is 2 times 1 over square root of 3 cubed. And thus from there we can do some simplification at this point if we want. We do know, trying to see if we can get rid of this square root of 3 here, because we know that 6 is 3 times 2, so that would be square root of 3 times square root of 3 times 2. Let's fix that. Times 2 there. All that over square root of 3. And we know that square root of 3 cubed is like multiplying square root of 3 times itself 3 times. So that would be the same as 2 over 3 root 3. And so that would get rid of that. 2 times square root of 3 minus 2 over 3 root 3. And I guess I'll just do this to rationalize. It would be 3 root 3 divided by 3 times 3 root 3, which that would just be 9. And we have, if we can factor out the 2 times square root of 3, that would just be 1 minus 1/9, which that would just be 8/9 there. And so all that will just simplify to 16 times square root of 3 over 9. And thus, the second part of this question is our inflection point will be at the value of natural log of 1 divided by square root of 3, comma, 16 times square root of 3 over 9. And that would actually be our point. Okay. All right, so I know this looks like a lot of work, but it's only a lot of work because I'm being very particular on showing every step. Of course, you're free to use more scratch paper in answering questions like this. But as long as you show me where your actual x and y value from your inflection point are and the interval, and the work is supported for that, it could be abbreviated some, but as long as there's enough work to kind of follow so that I know that you know what you're doing, then that will be acceptable. Okay. All right, so let's move on to the next question. All right, so for question number 8, we're given a graph of the derivative of some function. And what we want to do is sketch a graph of the original function as well as its second derivative. And so we have a Cartesian plane for the original function here. And if we look down, we see that we have a Cartesian plane for the second derivative. So what I'm going to do is actually start by going with the first derivative to the second derivative, because that's actually easier. And we're going to see how to sketch the graph of this. So remember that whenever we talk about taking the derivative of a function, what we're doing is tracking the slopes of the tangent lines. Or put another way, we're tracking when the graph is increasing, when it's decreasing, and when it's constant. So the first thing that we want to note for our graph f prime going to f double prime is, where does f prime have horizontal tangent lines? Because where f prime has horizontal tangent lines, that lets us know that f prime is constant there, meaning that the graph is neither increasing nor decreasing. Why that's important to us for the second derivative is because, or any derivative for that fact, is that for some original function, wherever you have a peak or a dip, so this is where you would have your peak at, and that's where you would have your dip at, that's going to tell you where you have your x-intercepts for the derivative. So if we come down here, we see that we'll have an x-intercept here. And if we come here, this is slightly past -4, so right there. And so if we notice here, the slopes of the tangent line are increasing here and decreasing there. So that means the slopes of the tangent line are positive and then go to negative. and right along at this x value, the slopes of the tangent line go from being negative to positive. And so that's important to us as well, because for the derivative of any graph, when the slopes of the tangent line are positive, we graph that above the x-axis. And when it's negative, we graph it below. Or put another way, when the graph is increasing, we draw the derivative above the x-axis. When it's negative, we draw it below. So now that we have that, we know that for the derivative of f prime, the graph is going to have to go from above the x-axis to below. And we know for this particular dip, it's going to have to go from below to above. So that much we already know. Now, the other thing that we have to find out is, now that we kind of know that the graph's going to go like this and go like that, where our inflection point is. And so for this question, we're kind of left up into interpretation because we don't have an actual algebraic version of f prime to give you. So I'm just going to guess that my inflection point is here. And we know that an inflection point is the point where concavity changes, granted that the point is defined on the graph. So our graph is concave down up to this point, and then it's concave up. So what that means to me is that the slopes of the tangent line start at 0 here, and then they decrease, and they decrease some more here. At the inflection point, that's where the slopes of the tangent line stop decreasing more. Okay, so it's kind of like looks like this: 0, then decrease, 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 and at that point it stops decreasing. And now after the inflection point, it starts to turn back more like this as far as the slopes of the tangent line are concerned. So here, at this point, we're going to map this down to some point right here, and that's going to communicate to us that for the derivative, the slopes of the tangent line stop decreasing more, or stop getting more negative, I should say. Okay, so I'll say that again. So at this point, the slopes of the tangent line stop getting more negative, or the graph stops decreasing more and more. And so this is where that particular graph will bottom out. And so now that we have that, everything else that we draw pretty much follows suit. So we just come and draw, and we see that this is going to look like a quadratic function. And of course, the key to let us know that is that we know that this particular graph looks cubic anyway. It could be of high or odd degree, but it does look cubic. So we know that if we have something that looks cubic as far as the original function is concerned, we know if we took the derivative of x cubed, it would be 3x squared. So we know that whatever comes down here for the derivative of something that looks cubic is going to have to look in some kind of way quadratic. Okay. Now, I'm not saying that this is the exact function for what we see here, but I'm just kind of giving you a sanity check to know that, hey, if I have something that looks cubic, when I draw the derivative of that, the derivative is going to have to look quadratic somehow. Okay. All right, so that takes care of the first derivative to the second derivative. Now let's go back up and talk about the original function to the first derivative. So now everything we just looked at, we have to look at backwards now. Okay, and so I'm going to erase what we currently had here so that we can have a clear graph for drawing the original function. All right, so now that we are looking at the derivative and trying to get the original function, everything that we have to think of is going to be backwards now. So what that means is that now the first place that we're going to look at is where we have our x-intercepts for our derivative. And that's important because the x-intercepts are going to let us know at what x-value locations we have a peak or a dip in our original graph of f. And so we see that here we know that the derivative is tracking the slopes of the tangent lines, or when the graph is increasing and when is it decreasing. So we see here at this x-intercept, which I'm believing is something like -7 here, the graph goes from being below the x-axis to above. And at 0, it goes from above to being below. And then at about almost 3 here, it goes from being below to above. So what this tells us, at x equals -7, the graph goes from being decreasing to increasing. So that looks like a local minimum. And at x equals 0, it goes from increasing to decreasing. So that looks like a local maximum. And then, of course, here at almost 3, again, goes from decreasing to increasing. So that's going to look like a local minimum. So here we're going to just pick some places. Really doesn't matter where, because we don't have an algebraic version of f prime of x. So I'm just going to pick here. Let's say at x equals -7. I'm just going to line it up as much as I can and say about right here, I know that I'm going to have a local minimum or a dip in my graph. At x equals 0, I'll come about right here and say that I'm going to have a local max or a peak in my graph. And then I'll come back here at right before 3 and then say, let me have another local minimum. I'll just do that. I'll probably I'm going to move this up some. Give me a little bit more room to draw. All right, so that's what we have. So now that we've taken care of where we have our peaks and our dips for our original graph, the second thing that we want to figure out is where do we have our inflection points for our original graph. And we saw from when we did the first derivative to the second derivative, and I'll scroll back down there so that we can see that. We saw that here for the derivative, it's wherever the derivative bottomed out, that sort of mapped up to where we actually had an inflection point. So here we're thinking backwards. We have the place where the bottom either tops off or bottoms out, and so now we need to translate that into a particular inflection point for our graph. So let me get this steady here. So we notice that we have a peak here for our derivative and a dip there for our derivative. So here, this should map up to, and I'm just going to pick a point about right here. That's going to be our inflection point for those interval x values. And then right here, this should map up to, let's just say about here. And that will be an inflection point for that next set of x values. Now, we notice here that this peak here is telling me that the graph of the original function stops increasing. So the slopes of the tangent line stop getting more positive there. So that means that I would need to draw, yeah, I messed that up pretty good, didn't I? So let me erase all of that. Try that again. Basically, I need to draw a line segment that's going to be positive, kind of like that. And of course here, bottoms out, it's below the x-axis, so I need to draw a line segment that's going to be negative, like that. And that's still not looking the way that I really want it to, so I'll just make it look like that, okay? So in general, we know that we have to have a graph that's going to have to start up here, eventually come down, kind of go through inflection point right here, come up, come down, bottom out, and come back up again. So when we draw that out, it'll look something like this. Inflection point there, come up, inflection point there, come down, and go like that. And so in general, this is how we take the graph of the derivative and draw the original function as well as its second derivative. So let's move on to question number 9. All right, so for question number 9, we're asked to find the x values for which the given function is increasing, as well as the x and y values for all local maximums and or local minimums. And so when we talk about local max and local min, we know that what we're talking about is where the peaks and dips of the graph are. And we can identify those where the slopes of the tangent lines are horizontal. So for us, what that means is we take the derivative of our function and set it equal to 0. And at those critical values, we know that we either have a peak or a dip. And so what we want to do is figure out exactly what is the corresponding y value so that we'll know whether we're dealing with a peak or a dip. And we also need to verify at each x value location whether it is a peak or a dip. And so there's 2 ways we can do that. We can use what's called the first derivative test, or we can use the second derivative test. I'm going to perform both of those for you so that you can sort of choose which way works best for you. And in doing that, you'll know how you would want to answer a question like this. So the first way I'm going to do this is by using the first derivative test. So regardless of what we do, we need to find out what the first derivative is. Okay, so the first derivative, we take the derivative of negative 4x cubed. That will be a negative 12x squared minus the derivative of 6x squared is just 12x. Derivative of 24 is just 4. And we know that the derivative of 1 is just 0. So we won't write that. At this time, I'll go ahead and factor out a negative 12 out of each term. So that'll leave me with x squared plus x, not 2x. So let me erase that right quick. So it'll be x squared plus x minus 2. And of course, if I factored out this quadratic expression here, that would factor out to maybe x plus, x minus, and I would probably put the 2 here, the 1 there. And that checks out. Yep. So that's what this would factor into. So now we know that if we take the first derivative and set it equal to 0, then that just means that negative 12 times x plus 2 times x minus 1 is equal to 0, which means that x plus 2 is equal to 0, or x minus 1 is equal to 0. And of course here, we know that means x is equal to negative 2, or x is equal to positive 1. So these are our critical values, or locations where we know we have a possible peak or dip. Now using the first derivative test, and let me make sure that looks right. So using the first derivative test, what I'm going to basically do is do test intervals to perform that. And I know that these are going to be my critical values. So -2 and 1. And so I'm just going to choose some test values in between here. And I know that if for the first derivative for a particular value of x, if the answer is positive, then I know that the graph is increasing. If I know that I get a negative value, then I know that the graph is decreasing. And if I'm going from increasing to decreasing, then I know I have a local max. And if I go from decreasing to increasing, then I know that I have a local min at that particular x value. So I'm going to use the increasing decreasing test to sort of back my way into the first derivative test. Okay. All right, so let's go ahead and choose some test values. All right, so we just want to choose some values in between here. So I'm just going to pick something easy like, if I can ever get it to work, -3, and I'll pick 0 here, and I'll pick 2 here. And so those will be the values that we use. So let's start with f prime of -3. And again, all I'm concerned about is whether the answer is positive or negative, not even really what the answer is itself. So here that will be a -12, and that will be -3 plus 2, and -3 minus 1. And so I see from here that I end up with -12, which is always negative, -3 plus 1, which would be negative, and -3 minus 1, which would be negative. So my result is negative. So from there, I know that my graph is going to be decreasing from x equals -infinity to right before x equals 2. So now we do the same thing, and we plug in 0 or evaluate the derivative at 0. And so again, we'll just plug in, and we see that we have a negative number times a positive number times a negative number, so that result is going to be positive. So that means our graph is increasing. So we can see right now that at x equals -2, what we end up having is a local minimum at x equals 2. So that much we already see here. So I'll go ahead and write that. So local min at x equals -2. Okay. So now we go ahead and plug in or evaluate the derivative at 2. And of course we have a negative times a positive here and times a positive there. So we end up with a negative answer. And so thus it tells us that the graph is decreasing again. And in between at x equals 1, we see that we're going to have a local maximum at x equals 1. So here we've verified that at x equals -2, we actually have a local minimum, and at x equals 1, we have a local maximum. So now what we're going to do is actually figure out what those corresponding y values are at x equals -2 and at x equals 1. All right, so plugging in -2 into our original function, we have a -4 times -2 raised to the 3 minus 6 times -2 raised to the 2 plus 24 times -2 plus 1. And let's make that look a little better there. All right, so with that, of course, -2 cubed is a -8, and -8 times a -4 is a +32. 2 squared is 4, and 4 times a -6 is a -24. 24 times -2 is a -48, and then we have plus 1. So from there, we know that 32 minus 24 is +8, and 8 minus 48 is going to give us a -40, plus 1 is 39. So for us, this means that we have the point -2, -39, and this will end up being our local minimum, point. So let's do the same thing again with 1. So just plugging in 1. And we'll see from here, 1 cubed is 1, times a -4 is a -4. And then 1 squared is 1, times a -6 is -6. Plus 24 plus 1. Of course, -4 minus 6 is a -10. And 24 plus 1 is a 25. So we get -15 as an answer. And thus our local max will be at the point 1, positive 15. Yeah, that is my mistake there. So, and that is our local max. So we've answered 2 of the 3 questions that we were originally asked. We were asked to find the x and y values for the local maximums and minimums, and we were also asked when is the function increasing. And so we've actually answered that because we know from when x is -2 to 1, our function is increasing. So we can say f of x, f prime of x is greater than 0. That is to say, f of x, that didn't turn out too good. So let's try that again. F of x is increasing and then of course x values would be from -2 to 1. So this would be the answer to our third question then. So we have local min value and point, or local min location and point, local max location and point, and then of course where our function is increasing. So let's move on to the next problem to answer what it's asking for. So the problem reads, a person who is new on an assembly line performs an operation in t minutes after x performances of the operation. So in other words, as the people do the operation more and more times, they basically get faster in doing it. Okay, so the minutes that it takes for them to complete it will be decreasing, and we see that as is given by this particular function here. So that function is modeling how many minutes it takes for them to do a particular operation after doing it X number of times. And it says if dx over dt is equal to 3 operations per week, or if we translate that, if the number of performances of the operation increases by 3 operations per week, where t is time in hours, then we want to find what is going to be d of big T over d of little t after 81 performances of the operation. Or if we put that another way, we want to find out what is going to be the rate of increase of decrease of how many minutes it takes for them to do a particular operation after doing 81 performances of that same operation. Okay. All right, so the first thing that we need to do is understand that we're going to have to take the derivative of both sides of this function here with respect to little t. And before we do that, we want to make sure that t is written in a way that is easy for us to take the derivative of it. So we know that this 1 divided by square root of x is the same as 1 divided by x raised to the positive 1/2, which we know we could rewrite as x raised to the negative 1/2. So we want to make sure that we have that in place first before we take the derivative of both sides with respect to little t. So let's go ahead and do that now. That will be 5 times 1 minus x raised to the negative 1/2. I'll go ahead and get rid of this here. Oops. Just erase that. All right, and so now, at least on this right side here, we know that we're going to ignore that constant. And we're just going to have 1 minus x raised to the negative 1/2. And if we take the derivative of 1 is just 0. And the derivative of, oh, this should be plus, not minus. So let's make sure that we don't make that mistake. And here that should be a plus right here. So whenever we take the derivative of 1 with respect to t, that'll be 0. The derivative of x raised to the negative 1/2 will just be a negative 1/2 x raised to the negative 1/2 minus 1. And since the variables don't match, we know that we're going to have to do the chain rule, where x itself is understood to be a function of t. So that is where the derivative of x with respect to t will come into play. And we will have that. So now what this means here is that just d of big T over d of little t is equal to 5 times, and this will be a negative, forgot about the 1/2 there. So negative 1/2 x raised to the negative 3/2 times dx over dt. And we could rewrite that as 5 times, well, let's say negative 5/2 times 1 over square root of x cubed, because x raised to the negative 3/2, that's how we would write that in root form, times dx over dt. So now to finish up, we now need to plug in the given value. So we know that x is going to be 81, because we're trying to figure out what is the rate of change of how many minutes it takes them to do this operation after doing it 81 times. And we know that dx over dt is going to be 3. So when we do that, of course, that's the 5/2, and we have the 81 cubed there, and dx over dt is just 3. So at this point, it's just algebraic, well, just really not algebraic manipulation, but just simplification. So we know that square root of 81 cubed is just square root of 81 multiplied times itself 3 times. And here I know I'll just use times 3. So we know that square root of 81 is just 9. And from there, we know that this is just 5/2 times 3 over 9 times 1 over 81, because we know square root of 81 times itself is just 81. This will reduce to 1/3. And we'll come over here, and this will be negative 5/2 times 1 over, and we'll just say 3 times 81. Well, actually, make it a little bit more simple on ourselves. We'll just say 2 times 3 is 6. We'll do it that way. And then do that with 81. And then 81, messed up that 5 real good there. And so 81 times 6 will just be 486. So let's finish this out. And the units for that, of course, will be minutes per hour. So that means that after doing it 81 times, the rate of decrease in the amount of time that this person performs the operation is -5/486 minute per hour. And so just to kind of give you an idea of what that number is, that's about, changes about -0.010288, so on and so forth. So you can see after doing it like 81 times, there's not going to be much of a decrease in the amount of time that person is going to improve on their time of doing that particular operation on the assembly line. Okay. Okay, so this is the end of the actual review that I have prepared here. However, I do want to illuminate a few more problems, just depending upon what version of the exam you get. I do want you to be aware of some of these other type problems that you may get that did not necessarily appear in this review. And so how I'm going to do it is I'm going to go to the notes to where I have problems worked out that are similar to the ones that you'll see depending on what version of the test you get, so that you're just aware of them. So I'm going to break away from this now and go to some of the examples. Okay, so depending on what version of the exam you get, you may get an inventory control type problem. For those of you that are in the business calculus course I'm in, this will be in section 12.6. And the way that the problem reads will be very similar to what you see here. The only thing that's different is it just depends upon what it may ask for. So for this problem, it says a paint manufacturer has a uniform annual demand for 16,000 cans of paint, cans of automobile primer, sorry. And the cost is $4 to store 1 can of paint for 1 year, and $500 to set up the plant for production of the primer. And so that $500 is for tooling the machines, materials, all that stuff to be able to make just 1 can of primer. And we want to know how many times a year should the company produce this primer in order to minimize the total storage and setup costs. Okay, so we need to know how many times we need to resupply or re-up everything so that we know that we can minimize those total storage and setup costs. So the first thing that we need to be aware of is the assumptions that are going on here. So first of all, the total cost is going to be the sum of the product of the setup cost times the number of production runs. So in other words, how much is it going to cost to do each setup times the number of production runs that we're going to run. And we also want to add that to the storage fee per can of paint multiplied by the average amount of paint primer in storage. And so this is where the assumptions come in. So if you haven't read your textbook, or if you haven't worked out problems like these, you need to make sure that you know these assumptions. Okay. So the assumption is that if we are making this automobile primer, that we're selling them at a linear rate, which means demand is being consumed at a linear rate. And so this picture that I have here shows that at the beginning of the year, we have Y number of automobile primer cans in storage, and then we linearly have those consumed. And then the first re-up for the production run, we'll do that, and we'll get Y number of cans of automobile primer again, and we decrease linear. We keep going up, and we keep going up. Okay, and we know that for each production run, the demand of the primer is soon to be depleted uniformly, which is another way of saying linearly, from Y cans to 0 cans. And so that's the assumption. Below, you also see that we define X as the number of production runs and Y as the number of cans of automobile primer per production run. Okay, and we know that the total demand here is going to be 16,000. I believe that's what that said. 16,000. So yeah, this should be 16,000, not 1,600. So our total cost here is going to be 500x plus 2y. And so we know from the setup cost, we were told that was 500. So that will be 500 here times the number of production runs. Of course, we define that as X. The storage fee costs $4 to store 1 can of paint for 1 year. So that's be $4 per year times the average amount of primer that we will have in there. And I'll just put a 4 here to make that easier to deal with. And of course, the average amount is this amount here, which is however much we have in storage divided by 2. Okay? And of course, 4 divided by 2 is just 2. So that's how we end up with total cost is going to be 500x plus 2y. Okay? And so since we're looking for the number of production runs, we need to write y in terms of x. Okay? So we're looking for that. So everything needs to be in terms of production runs so that we can find that. So moving forward here, we know that 16,000 is the total demand for the year. And of course, we can find that out by doing the number of production runs multiplied by the number of cans of paint primer per production run. Okay? Or we can just simply say like this: number of runs times the number of cans per run. And of course, those units reduce to 1. So we just end up with the number of cans. And thus, we can write the number of cans that we get, or the number of cans per production run. We can write that in terms of X, which is going to be the number of production runs. So now we have something to replace Y with. So now we take all this and just substitute it for Y. And now we have a cost function in terms of just the number of production runs. And so now what we want to do is minimize that. So of course, whenever we talk about minimization and maximization of cost, we want to take the derivative and set it equal to 0. And of course, if we find that the value of X or values of X that satisfy this equation is such that it's equal to 0, and we find that we have a minimum, then of course we know we have a local minimum. Of course, if we find we have a maximum, then we know we have a maximum. And of course, we can do that by either the first or second derivative test. So take the cost function, get the derivative of it, and then after that set it equal to 0. And then of course after that we see that X equals 8. That is going to be our critical value. Okay? And so now at this point you are not done with the problem. Okay? All you've identified here when you say X is equal to 8 is that the 8 production runs is either going to minimize cost or maximize cost. And what you need to do is to verify by using either the first or second derivative test that that's actually going to be a global min in this case. In other words, it's going to be minimum. So I come here and I actually work it out both ways by using the first and second derivative test. So if we're looking back at our derivative for our cost function, and I'll just use this since I have the same thing here. Using it for the first derivative test, all I do is I just plug in 1 into my first derivative, and I plug in 10 because I chose those as my test values on either side of my critical value, which was X equals 8. and I see that the cost are the rate of change of cost are negative when production run is 1, and when number of production runs is 10, I see that the rate of change of cost is positive. So that tells me I went from cost decrease, rate of change of cost decreasing to increasing, so I have a global min. And so this verifies that x equals 8 is indeed a global minimum, and thus at 8 production runs, we're going to minimize cost. Okay. For the second derivative, how you would do it is you would still find out what the critical value would be for the first derivative, which is what we found up here, x equals 8. But here for the second derivative test, we would take the derivative of the first derivative to get the second derivative, and then plug in that particular critical value. And by doing that, this is what we end up showing. If we show here that the cost at that particular value of x is positive, then we know that C of x was concave up, and this point right here was a global minimum. Okay, and just the opposite, if we see that cost for the second derivative, try to do that, for the second derivative is negative, then we know that the cost function looked like this. It was concave down, and that's going to be a global maximum. And of course, in this case, we see that it ends up being positive, so that meant that the function itself was concave up, and so critical value let us know we have a local minimum, and since it's the only one, it's also a global minimum. Okay. And so once we verify that, then we can say the company should have 8 production runs per year in order to minimize total storage and setup costs. Okay? So again, please make sure that you study this, because depending upon what version of the exam you may have, you may get this particular problem. All right, so let's look at another problem that you may encounter. All right, so for this next question, this is a classical, area problem where we're trying to figure out how to either, maximize area or minimize cost. And in this case, we're talking about minimizing the cost of trying to fence some area around. And so here we have a farmer that wants to fence an area of 1.5 million square feet in a rectangular field, and then divide it in half with the fence parallel to one of the sides. Okay, and that's probably to separate the different types of crops or animals or whatever it is that they are trying to produce. So we want to know, how can the farmer do this so as to minimize the cost of the fence? Okay, so we know that the less amount of fencing that the farmer actually puts up, the less he or she's going to have to spend in that. Okay, so we know that the total fencing area is going to be 1.5 million square feet, and we also know that area is just x times y. Of course, I've drawn this figure here to kind of give us an idea of what's going on. So area in general is just x times y, or we'll say length times width. We know that the perimeter, if this side is x, then this side is x2, and that side is x2. And of course, this entire side is going to be y, just like this side is. Okay. So we know our perimeter is, in other words, the sum of all the sides, or for all the fencing that we're going to lay, is going to be 3x plus 2y. Okay. And we know that whatever that is, we don't know how much of that we need to put up, but that is the point of the problem. But we do know that area can be used and rewritten to be written as y in terms of x. Okay, where we're given what the area is, so we have that constraint. So if we come here, the perimeter is just going to be 3x plus 2y. And of course, y is just the same thing as a divided by x. So see how that now turns into this because of what we see here. And now we have perimeter in terms of x, or in terms of this side here. So then from that point, we will let the perimeter function be this, where we understand that the domain of that function, from how we've modeled it so far, will be from, really it shouldn't be a bracket here. It should be parentheses from 0 to infinity, because we can't have a side that is exactly 0 feet in length. So moving on here, we will need to find out what the derivative of the perimeter is and set it equal to 0. And then the critical numbers that satisfy that equation here will actually tell us where our perimeter can be minimized and or maximized. Okay. And so we'll go and take the first derivative of our perimeter function, which is here. And of course, when we have this is just, and I'll just rewrite this here. Perimeter is just 3x plus, and this is 3 times 10 raised to the 6 times x to the negative 1. So we're really just taking the derivative of that. And when we take the derivative of it, that would just be 3 minus 3 times 10 raised to the negative 6, x raised to the negative 2. And of course, that turns into what we see here. And then from there, if we add this term to both sides, we get 3 times 10 raised to the 6 divided by x squared equals 3. And then from there, we just do algebraic manipulation to solve. And we see that x ends up being 1,000 feet. So that is our critical value. And so we know that at 1,000 feet, either we are minimizing or maximizing the perimeter, which means in turn we're also minimizing or maximizing the cost there as well. And we need to verify that. So the way that I went about doing it in this problem was that I used the first derivative test, and here I set up my test interval. Of course, 1,000. I know that at 0 here, this should really be a parenthesis, not or a closed point. Yeah, it should be this or an open circle there. So I'm going to change that as well. And so from here, I chose a value of 100, and then over here, chose a value of 2,000. And I see that whenever I found out what the derivative of the perimeter was with these values plugged in, these are the values that I got. Of course, it shows me that the rate of change of perimeter is decreasing at 100, increasing with 2,000. So going from decreasing to increasing tells me that I have a global minimum in this case, since it's the only critical value that I have. And so now we see that here we have a global minimum at x equals 1,000 feet. So therefore, to minimize the cost, we know that x is going to have to be 1,000 feet. So that's going to have to be the length of the width side, and of course the length. We just plug in 1,000 back into our original equation for y, which was just a divided by x, or 1.5 times 10 raised to the 6 square feet divided by x. And we see that we end up getting 1.5 times 10 to the 3, which is the same as 1,500 feet. So if we come back up to the top here, we know that x is going to have to be 1,000, and y here is going to have to be 1,500. So we got 1,500, 1,500, 1,000, 1,000, 1,000. And doing it that way will definitely minimize the cost. involved in putting up this fencing. All right, so let's look at one last example. All right, so this will be the last problem I present, and this is another example of problem where you will need to this is an optimization type problem. And in this case, we're trying to figure out how much rent a manager should charge to maximize revenue. So for the last two problems, we did minimization. This problem, we're going to do maximization. So, I do have one other problem. So after this, I'm going to show you one more just to make sure that you're aware of that one as well. So we have here a manager of a 100-unit apartment complex knows from experience that all units will be occupied if the rent is $800 a month. The market survey suggests that on average, one additional unit will remain vacant for each $10 increase in rent. And what rent should the manager charge to maximize revenue? Okay. So the way that I go about this is sort of a more of an algebraic approach to start off with. So when I look at this, I say I know if the price is going to increase by $10, then the rent is going to be $810. Okay, and then if the price is going to increase by $0, then the rent is $800. So basically, I took the information that was given to me to come up with one point and did the $10 increase to come up with another point so that I know that my rate of increase is 10. And so now if I want to form a linear price demand equation, then I know that I can do that simply just by noting that this point here is going to be a y-intercept and that my slope is 10. Didn't necessarily have to do this, but I just did it because at the time when I worked this problem, that's how I was thinking. So my price demand function will be 10x plus 800. And so we also know that for the vacancy, and vacancy is, of course, how many people are actually staying in the apartment at that particular time. We know that vacancy is going to be totaled out at 100, but we know that this would be the formula for every $10 increase in rent. So here we can say that the revenue is going to be the amount of vacancy times the price of the rent. And so here we're tracking demand by vacancy. So here we see that vacancy is just 100 minus x. The price is just 10x plus 800. And when we multiply all that together, we see that we get this quadratic function that opens down. So we know from algebraic terms here that we're going to have a maximum for revenue. And of course, this is a calculus course, so we're going to do it the calculus way. So to find the rent the manager should be charging, we're going to first find out what value of x is actually going to satisfy the rate of change of revenue being a maximum. Because we know that whenever the rate of change of revenue is going to be equal to 0, that's going to let us know whether we have a maximizing revenue or minimizing revenue. And in this case, we kind of know it's going to be maximizing, but we still have to verify that by either using the first or second derivative test. So we take the derivative of our revenue function and we get negative 20x plus 200. We solve that and we get x equals to 10. So we know that, again, x is going to be the number of increases in rent. So this essentially says that, hey, we should be increasing the rent by 10 multiples of $10, which is $100. Okay, so we use it as our critical value, do some test points around, and I use test point of 1, and over here I use test point of 20, and we see that revenues are increasing if I only do one multiple of $10 increase, And if I do 20 multiples of $10 increases, which is basically $200, and I'm going to be decreasing revenue at that time. So here we see that going from revenue increasing to decreasing looks like a global max. And thus, that verifies that revenue will be increasing from 0 to 10, decreasing from 10 to infinity, and that we have a global max at x equals 10. And thus, what that essentially is going to tell us is how much should we be charging for rent. We know that we need to bump up the price 10 multiples of 10 from the 800 that we were at, and thus that gives us $900. So if we charge $900, that will maximize the amount of revenue that we can get from that particular property. All right, so let's move on to the last example. All right, so the last problem that I wanted to do is one that has to do with related rates. And so you'll see something of this ilk won't exactly be this problem, but something like this, okay? So it says a retail store estimates that weekly sales S and weekly advertising costs X, both of which are in dollars, are related by the function that's given to us. And the current weekly advertising costs are $1,000, and these costs are increasing at a rate of $200 per week. Okay, so here we know that since X is advertising cost, we know that at this snapshot in time, X is going to be 1,000 for us. We also know that the costs are increasing at a rate of $200 per week. That lets us know that rate, anytime we're talking about a rate, that's a derivative. So the rate of change of advertising costs with respect to time is going to be $200 per week. And so now, of course, we assume that X is a function of T and S is a function of T as well. So now what we're trying to find is the current rate of change of cells. So that's going to be the rate of change of cells with respect to time. So here, we just need to take the derivative of both sides of this particular equation with respect to T. And so when we do that, this is what we will get. On the left side, we just get ds over dt. And of course, the derivative of 50,000 is just 0. We ignore the constant 20,000. And the derivative of e raised to the negative 0.001x. Remember, x is a function of t. So we know that since the variables do not match here, we are going to have to use the chain rule. So in doing the chain rule, we know that the derivative of e to the blah is just e to the blah times the derivative of x of t with respect to t. That would just be the derivative of x with respect to t. And that's where we perform the chain rule. So of course, simplifying all that, we just get a negative 20,000. Oh, sorry, yep, I forgot. Before I do that, let me start this over. So we have to do 20,000 here times, we need to do the chain rule here. But to do that, we have to take the derivative of the outside function, which is e to the blah, times derivative of the inside function. And the inside function itself is d over dt of negative 0.0001x. And so now, in doing this, of course, we ignore the constant there, so that would be negative 20,000 times a negative 0.0001, and then we're just taking the derivative of x with respect to t, so that's where the dx dt comes in. So we'll have all that e raised to the point 0.0001x times dx over dt. All right, and so from there, we'll say ds over dt, where x is going to be 1,000, and dx over dt, which I'll just call x prime, will be 200. I'm just going to put everything in. So negative times a negative is a positive, and 20,000 times 0.0001, or read differently, 1/10,000th, is just like saying 20,000 divided by 10,000, which is just 2. That'll be e raised to the 0.0001, and then you put in 1,000 for x, times dx over dt is 200. And so then from there, 200 times 2 is 400. And it'll be e raised to the 0.1, because 1,000 times 1/10,000th is just 100 divided by 10,000, which is just 0.1. And of course, this will come out to be approximately, I'll just go ahead and type it in right quick. Let's see. It's about 361.93. So we'll see here that rate of change of cells will be increasing roughly about $361.93 per week. So that's how we do that problem. So again, I know this exam review was long, but I wanted to make sure that you saw just about everything that you can expect, so that you'll be well prepared for these exams. And so if you have any questions, for those of you that are taking my course, please let me know. If you're watching this YouTube video and you still have questions, just leave me a comment and I'll get back to that as soon as I can. All right, thank you so much.